Hello, and welcome to a video on piecewise functions. All right, so this is one topic that you will cover much more in a pre-calculus and even in a calculus class, but it's one thing that it's kind of an interesting concept to develop from this course because it does take into account the material we just studied on transformations of the parent functions. All right, so here's an example of the equation of a piecewise function. All right, so all this is saying is there's some function that we can't just write with one equation. All right, so there's some function that we follow a linear equation on this domain, then we consider the constant function y equals 2 on this domain, and then the quadratic function written here on that domain. So we've just kind of done this recently. The first problem on your last quiz, actually, was a quadratic function that you were only drawing on a specific domain. And the purpose of that kind of problem is to allow you to do or to understand a problem like this. All right? So here's how we would draw this. So that's really the main goal of the video. If you're given a piecewise function like this, how to draw the graph. All right? You should be able to go the other way also. If I gave you the graph of the piecewise function, how to write the equation. And it is written in several parts. Usually there are 2 equations that define the piecewise function, or 3 or 4, even more, but usually 2 or 3. To keep things practical, kind of short. All right, so of course I don't have a grid up here. I wish I've got to invest in a whiteboard that has a grid on it. So got to make that happen. Anyway, okay, so we're going to start with the top function. It doesn't really matter which one you start with, but I usually start with the top and go down. So the equation y equals 4 plus x is the same as the equation y equals x plus 4. If you remember from Algebra 1, that is a linear function that has a slope of 1 and a y-intercept of 4, right? So that equation would look like, all right, a y-intercept of 4, let's say, is right there, and the slope is 1. So, okay, we're going to go up 1 over 1, up 1 over 1. It's a diagonal line through that point. So it'll have like an x-intercept here at -4 and a y-intercept at 4. So like that point would be 0, 4. This point, -4, 0. This is the way that graph would look, right? But we're only considering, and that should be a perfect diagonal line. Human error, right? But that should be a perfect diagonal line. The slope is 1, so we go up 1 over 1, or up 4 over 4, whatever you want to think about, or however you want to think about it. But we're only considering that line for values of x that are less than -2. So actually, all this is gone. All right? We're going to stop this where x is -2. All right? So, and okay, it's not including. So we're going to have an open circle there, all right? Open circle. So where x is -2, that point right there, y, if you plug into the equation, -2, y would be +2. So that open circle there happens at the point -2, too. So if you're showing this graph, you do want to show the particular endpoints on each piece of the function, all right? So the first piece of the function is going to be a line, or a piece of a line, in this case like a ray, all right, that has an open circle here, and goes down like this forever. All right, so just to be clear, the line y equals x plus 4, or 4 plus x, is the full diagonal line forever, but we're stopping this at -2, right? This is like -infinity to -2. So all the way down forever up to that point, but not including it. All right, so that's the first piece of the graph. Now we follow this horizontal line. It's a constant function, right? Y equals 2 is that horizontal line on forever, where y equals 2. But we're not drawing the full line. That wouldn't be a function, right? If we drew the entire horizontal line, then the entire graph would fail the vertical line test, right? This piecewise function is a function. So you got to make sure that it does pass the vertical line test. So we're following the equation y equals 2 between those 2 values. So actually, because it happens to pick up right where you left off here, then for the next piece of the graph, this does actually get filled in, all right? So that can happen sometimes. Because this point, right, y equals 2 when x equals -2. So coincidentally, even though it wasn't filled in this one, yeah, y equals 2 is a point on the next part, all right? So where x is -2, y equals 2 because of the middle one. And all the way until 0, we have y equaling 2. Including 0? No, not including 0. At that point, we have an open circle, right? So this should be an open circle. there. I hope I'm drawing those circles large enough. All right, so that circle was open, but it got filled in because of the middle piece, which is just a little horizontal line segment between negative 2, 2 and 0, 2, right? So we have this linear function, this constant function, which is technically a type of a linear function. It is a line after all. And the last part is this quadratic function, right? This is the parent quadratic function that was shifted 2 to the right and 1 down. Right? So the vertex is going to be at 2, negative 1. So let's ballpark where that would be. So x equals 2 around here. Negative 1 might be here-ish. So that would be the vertex, right? And then it's going to go on forever, right? X is greater than or equal to 0 means like a bracket 0 to infinity. All right? So to figure out how to draw the rest of this, we know the vertex is going to be down there at the point 2, negative 1. But okay, where x is 0 itself, plugging it into the equation, which is something you kind of have to do here, 0 minus 2 is negative 2, squared is positive 4, 4 minus 1 is 3. So 0, 3 is going to be a point on our graph. All right, so that is going to be a bold filled-in circle because of the or equal to. Right? So there's an open circle at 0, 2, but the filled-in circle, so this does not fill this in like it did previously, or it would pick up a little bit higher up, right? Because when you plug in 0 here, you get 3. So now, if you wanted to be exact, maybe you plug in 1 also to get another point between here, but I think it's sufficient. If we have the vertex, we know what the shape is going to be like. It's a parabola. So something like that, and on forever, right? Because it goes just greater than 0, or greater than or equal to 0. That's implying all the way to infinity, so we do have an arrow there, all right? So this is the graph of this piecewise function. And we can talk about domain and range also. We might as well, all right? But this is just how to graph a piecewise function. Notice how the vertical line test would pass. The only place it looks like it might get a little hairy is when x is 0, because it seems like there are 2 points where x equals 0, right? And then if there were, it would not be a function. But the open circle is not really a point on the graph, all right? So the value of the value of y when x is 0 is 3, not 2, all right? So just to make this clear, this is still a function, all right? It just has 3 pieces: linear, constant, quadratic. All right, so the domain, well, there's no value of x that we aren't using here, right? I mean, this is really just going from negative to positive infinity. Every x value from negative to positive infinity is being used, all right? There's nothing missing. Now, here at where x equals 0, we have what's called a discontinuity. The graph is jumping from a y value of 2 to a y value of 3. You have to physically lift up your pencil to draw this graph. But the x values do continue. Every x value from negative to positive infinity does have a corresponding y value, all right, including 0. So the domain is this. And so I do expect you to use interval notation. And the range also is the same. Think about it. The lowest point on the graph, well, it will go down here forever. The highest point on the graph, it goes up here forever, right? And every number for y is used in between, okay? Even though there's a hole there, open circle, hole in the graph, y does equal 2 everywhere in here, and then at this point here on the parabola. So, yeah, the range is also negative to positive infinity. With piecewise functions, you definitely want to use the graph to figure out your range, right? The domain we kind of already know. Just by looking at the intervals here, we know that every x value is going to be used, all right? So we have that. So hopefully this was a nice introduction to piecewise functions, and then in class, I'm going to give you several problems where I give you the piecewise equations and ask you to sketch a graph, and then also give you the graph and ask you for the equation. Thank you.